Somewhere in the mountains of Chile, a machine that was not even switched on yet saw something it was never supposed to see, before scientists announced it, before the world knew it existed, before humanity had a name for it. A visitor from another star system had already slipped past our sun, unnoticed, unannounced, moving too fast to belong to us, and one half-finished telescope, still being tested, still being calibrated, quietly took its picture 10 days before any one official pressed the alarm. Nobody told it to look. It looked anyway. For most of 2025, almost nobody outside a small circle of astronomers was paying attention to a mountaintop in northern Chile called Cerro Pachón. At 8,800 feet, in air so dry and skies so dark that engineers chose the location specifically because almost nothing on Earth interferes with what happens above it, a telescope had been rising for years, funded jointly by the U.S. National Science Foundation and the Department of Energy, at a cost that ran into the hundreds of millions of dollars. It was named after Vera Rubin, the astronomer whose work first forced the world to confront the existence of dark matter. And in the months before it was supposed to matter to anyone, it was still just being tested. Here is where it gets strange. A telescope in its testing phase is not supposed to make discoveries. It is supposed to be checked, calibrated, pointed at known patches of sky to make sure its mirrors are aligned and its camera is behaving the way engineers expect. This is the boring part, the part before the real science starts. Nobody expects headlines out of a calibration run. But sometime in late June of 2025, during what astronomers call its science validation phase, the Rubin Observatory was pointed at a specific patch of sky for entirely routine reasons, and in doing so it photographed something that had no business being in that image at all. 10 days later, a separate telescope, a NASA-funded early warning system built specifically to catch dangerous objects heading toward Earth, spotted something moving through the solar system that did not belong to it. Its path was wrong. Its speed was wrong. Nothing gravitationally bound to our sun moves the way this object moved. Within days, astronomers confirmed what the data was telling them. This was not a comet born in our solar system. This was not an asteroid that had always been out there, waiting to be found. This was a visitor, a physical object from another star system entirely, one that had been drifting through interstellar space for who knows how long, and had simply happened to pass close enough to us to be seen. Astronomers gave it a name, 3I Atlas. The I stood for interstellar. It was only the third such object ever confirmed in human history, but here is where it gets worse in the best possible way. When researchers went back through the Rubin Observatory's test data, back through the images captured during that routine calibration run in June, they found it already there, sitting in the frame, caught on camera, 10 days before the rest of the world knew to look for it. A machine that was not even finished being built had already seen a visitor from another star, and nobody realized it until after the fact. Think about what that actually means. This was not Rubin Observatory doing its job. Its job had not even started yet. This was a telescope in the middle of being tested, pointed at a patch of sky for reasons that had nothing to do with hunting interstellar objects, and it caught one anyway. Astronomers didn't find 3I Atlas with Rubin on purpose. They found it by accident, buried inside data nobody had originally been looking at for that reason. Read that again. The most powerful survey telescope ever built might have been the first eyes in human history to lay on an interstellar visitor, and it happened almost by luck, weeks before the instrument was even supposed to be operational. To understand why this matters, you need to understand what kind of machine we are actually talking about. This is not an ordinary telescope. At its heart sits an 8.4-meter mirror, but the real monster is what sits behind it, a camera roughly the size of a small car, weighing about 3,000 kilograms, containing 3.2 gigapixels of resolution. It is, by a wide margin, the largest digital camera ever constructed for astronomy. A single image from this camera is so large and so detailed that if you tried to display it at full size on a normal television, you would need hundreds of televisions arranged together just to see the whole thing at once. And this camera does not do what most telescopes do. Most of the great observatories in history have been built to stare patiently at a single point in the sky for hours or days, drinking in as much light as possible from one distant galaxy or one faint star. Rubin was built to do something almost the opposite. It is designed to scan over and over the same patches of sky again and again every few nights for 10 straight years, building what scientists have started calling a movie of the universe rather than a photograph of it. Every time it revisits a patch of sky, it compares what it sees now to what it saw before. And when something has changed, when something has moved, brightened, dimmed, appeared, or vanished, the system flags it instantly. This is where the story stops being about one lucky accident and starts being about something much bigger. Because a telescope that can notice change automatically across the entire visible sky, night after night, is not just a telescope. It is a detection machine for anything that moves, explodes, flares, or arrives. And in February of 2026, when engineers ran a live test of this alert system for the very first time, pointing Rubin at a patch of sky where previous surveys had already built up enough historical data to compare against, the result was almost hard to process. In a single night, the observatory generated 800,000 alerts. New asteroids. Exploding stars, flickering variable stars, distant galactic cores suddenly flaring to life as their central black holes fed on infalling matter. 800,000 individual events, flagged automatically in the space of one night, from a telescope that had not even begun its real survey yet. And this is where everything changes, because that number is not the ceiling. It is closer to the floor. Once the legacy survey of space and time, Rubin's 10-year mission, moves into full operation, scientists expect the system to generate as many as 7 million alerts every single night, 7 million individual notifications every night for 10 years, cataloging changes across the visible universe in something close to real time. No human being, no team of human beings, could ever manually review that volume of information, which means the real story of Rubin Observatory was never really about a telescope at all. It is about the birth of an automated, machine-driven early warning system for the entire sky, one that does not sleep, does not blink, and does not wait for a scientist to happen to be looking in the right direction at the right moment. Consider what that quietly solves and what it quietly creates. For most of the history of astronomy, discovery has depended on luck and attention. A supernova has to be caught while it is still bright enough to see, and if nobody happens to be looking at that patch of sky that night, it can burn out and fade before anyone even notices it happened. A dangerous asteroid can pass unnoticed simply because no telescope was pointed at the right coordinates at the right hour. This has always been the quiet vulnerability sitting underneath modern astronomy. We were never actually watching everything. We were watching pieces of everything at scattered times, hoping the important moments happened to fall inside our field of view. Rubin was built specifically to remove that vulnerability, and in doing so, it has already started rewriting what counts as a routine discovery. In its very first preliminary data release, drawn from barely a handful of nights of test observations, astronomers using Rubin's early data identified more than 11,000 new asteroids that had never been cataloged before, all of them confirmed by the International Astronomical Union's Minor Planet Center. Among them were 33 near-Earth objects, asteroids whose orbits bring them close enough to our planet to matter, that had never been detected by any telescope on Earth until this one found them almost as an afterthought during its testing phase. Sit with that for a second. 33 objects capable of crossing paths with Earth's orbit, invisible to every survey that came before, revealed in a handful of nights by a telescope that was not even fully operational. This is not a small correction to the catalog of near-Earth objects. This is a demonstration that our previous picture of what is out there, orbiting close to home, was incomplete in ways we did not fully appreciate until a machine built specifically to notice everything finally turned on and started noticing. And then there is the asteroid that should not, by the normal rules of physics, be able to exist the way it exists. Buried in that same early data, astronomers found an object roughly the size of 8 football fields, a solid half-kilometer chunk of rock spinning on its axis once every 1.88 minutes. That is not a typo, less than 2 minutes for a full rotation. To put that in perspective, most asteroids of similar size rotate over hours, sometimes days. A loosely bound pile of rubble, the kind of asteroid many objects of this size are believed to be, would be torn apart by its own centrifugal force at anywhere close to that spin rate. It would simply fly apart into smaller pieces, the way a badly balanced washing machine shakes itself to pieces at high speed. But this one hasn't. It is still there, intact, spinning faster than any object of its size that has ever been recorded. And researchers studying it now believe it may not be an ordinary asteroid at all. One leading theory suggests it could be the surviving fragment of the solid metallic core of a planet that existed in the earliest, most violent days of our solar system's formation, over 4.5 billion years ago, before that ancient world was shattered in some ancient, unrecorded collision, leaving behind a spinning fragment of its heart that has been tumbling through space, unnoticed for the entire history of the solar system, until this telescope caught it in barely a week of test observations. This is not chaos. This is not a fluke. This is a pattern. Every one of these discoveries, the interstellar visitor caught by accident, the 11,000 hidden asteroids, the 33 previously invisible near-Earth objects, the impossible spinning fragment of an ancient, shattered world, arrived not because Rubin Observatory tried especially hard to find them. They arrived because for the first time, we built an instrument sensitive enough, wide-angled enough, and consistent enough that it simply could not help but notice things that had been quietly hiding from every telescope that came before it. So think about what most people are not seeing in this story. It is not really a story about one telescope. It is a story about how much of the sky above us has been sitting there this entire time, completely unmonitored, completely unwatched, simply because nothing on Earth had ever been built with the capability to watch all of it at once. Every near-Earth asteroid Rubin has already found without even trying raises an uncomfortable question nobody likes to sit with for too long. How many more objects capable of reaching Earth's orbit are still out there right now, uncatalogued, simply because no one has pointed the right instrument at the right patch of sky yet? And this is where the story stops being just about astronomy and starts brushing up against something closer to planetary security. A telescope that can, almost by accident, reveal dozens of previously unknown objects capable of crossing Earth's orbit is not just a scientific tool. It becomes part of the infrastructure of planetary defense, the quiet, unglamorous effort by scientists and governments around the world to make sure that if something dangerous really is out there heading toward us, we see it coming with enough time to do something about it. The 11,000 new asteroids identified in Rubin's earliest test data are not simply an academic footnote. Each one is a small correction to a map that governments, space agencies, and defense planners rely on when they assess what risks the solar system actually poses to life on Earth. Once the full 10-year survey is running, astronomers expect Rubin to eventually catalog the majority of large near-Earth asteroids that exist, essentially completing a map that has been dangerously incomplete for the entire history of human civilization. But completing that map does something else, too. It means that for the first time, we may actually know, with real confidence, whether or not something threatening is heading our way, rather than hoping we happen to notice in time. That is not a small shift. That is the difference between blind luck and genuine foresight on a planetary scale. But here is where it gets more complicated. A machine capable of generating 7 million alerts a night, capable of tracking every visible change across the sky in near real time, does not just serve astronomers hunting asteroids. It becomes, whether intended this way or not, one of the most powerful surveillance instruments of the natural universe ever constructed. Every satellite in orbit, every experimental spacecraft, every object launched by any nation on Earth moves against the same backdrop of stars that Rubin is scanning night after night. A tool built to watch the cosmos does not stop watching just because something artificial happens to pass through its field of view instead of something natural. This is not a conspiracy. It is simply the nature of an instrument this sensitive. Noir Lab, the organization overseeing Rubin's operations, has been explicit that the primary purpose of the observatory is scientific. Dark energy, dark matter, the structure and history of the universe, the safety of our own solar system. But the underlying capability, an automated system capable of noticing anything that changes, anywhere in the visible sky, night after night, for 10 uninterrupted years, is the kind of capability that reaches beyond pure science, whether anyone intends it to or not. What most people are not seeing is that we have just switched on the closest thing humanity has ever built to a truly comprehensive nightly record of everything happening in our corner of the universe. And a record like that has value to a lot more people than just astrophysicists. Consider the scale one more time, because the scale is the part that keeps escalating the longer you sit with it. Scientists involved with the project have said plainly that Rubin is expected to collect more astronomical data in its first single year of full operation than every other telescope in human history combined. Not more than most telescopes, more than all of them. Combined, centuries of accumulated observational astronomy, all of it, potentially outpaced by 12 months of data from one machine on one mountain in Chile. And this is where the story pulls back out to something almost philosophical, because a data set that large cannot really be understood by human eyes alone anymore. Nobody is going to sit down and personally review 7 million nightly alerts. The scale has already outgrown human review. Which means the real story of Vera Rubin Observatory is not just the discoveries it has already made. It is the quiet admission built into the very architecture of the machine that we have reached a point where understanding the universe now requires automated systems working alongside human scientists, not replacing them, but filtering a volume of information that would otherwise simply overwhelm us. Here is what makes this genuinely uncomfortable to sit with. Rubin's full survey, the real mission, the 10-year legacy survey of space and time, only fully began moving into operation in the middle of 2026, months later than originally planned, after commissioning and technical checkouts took longer than engineers first expected. Which means everything described here, the interstellar visitor caught by accident, the 11,000 asteroids, the impossible spinning fragment of an ancient world, the 800,000 alerts in a single test night, all of it happened before the telescope was even doing its actual job. All of it happened during testing, during calibration, during the part of the process that is supposed to be uneventful. So the question that should genuinely unsettle you is simple. If the warm-up act alone produced an interstellar object caught by accident, a previously unknown population of near-Earth asteroids, and an object spinning fast enough to defy what we thought we understood about how asteroids hold themselves together. What happens when the real 10-year mission is actually running at full strength? What happens when this machine spends not 7 nights, but 10 uninterrupted years, scanning the same stretch of sky over and over, catching every flicker, every flare, every faint movement across the entire visible southern hemisphere? Astronomers are already preparing for an answer they cannot fully predict. The Dark Energy Survey collaboration has already begun using Rubin's early data to study hundreds of millions of galaxies, hunting for clues about dark energy, the mysterious force that appears to be accelerating the expansion of the universe itself, a force we can measure the effects of but still cannot explain. Researchers studying dark matter, the invisible material that appears to outweigh all the visible matter in the universe several times over, are hoping Rubin's decade-long survey will finally offer enough data to distinguish between competing theories that have remained stubbornly unresolved for generations. These are not small questions. These are some of the deepest unresolved mysteries in all of physics, and for the first time, scientists have a tool that might actually be powerful enough and patient enough to answer them. But notice the pattern one final time, because it is the same pattern that has repeated throughout this entire story. Every time Rubin Observatory has been pointed at the sky so far, even accidentally, even during routine testing, even before its real mission had technically started, it has found something nobody expected. An interstellar visitor caught before it was officially discovered. A hidden population of asteroids capable of reaching Earth. An object spinning in a way that challenges assumptions about how solid such things can be. If that is what a handful of test nights produced, the honest answer to what a full decade will produce is that nobody actually knows. Not with confidence, not yet. And that, in the end, is the real weight sitting underneath this entire story. We built a machine specifically because we suspected the sky was hiding more from us than we realized. We were right. It had barely finished being switched on before it proved that suspicion true, multiple times over, in ways that startled the very scientists who built it. The interstellar object was only found because someone thought to go back and check old test data on a hunch. The impossible asteroid was only noticed because the alert system happened to be active during those specific nights, which raises the quiet, uncomfortable question that no press release has fully answered. What else might already be sitting inside the data Rubin has already collected, unnoticed, simply because nobody has gone looking for it yet? Somewhere in Chile, right now, a camera the size of a small car is still scanning the same patch of sky it scanned last night, and the night before that, comparing what it sees against everything that came before, waiting for something to change. It does not know what it is looking for. It does not need to. It only needs to notice when something is different. And if the last 12 months are any indication of what the machine finds when it is barely paying attention, the next 10 years of its full, uninterrupted survey may end up rewriting more of what we think we understand about our solar system, our galaxy, and the forces shaping the universe itself than any single instrument in the history of astronomy. The only real question left is what it will find next, and whether we will even be ready to understand it when it does.